Okay, good morning. And so what we have in front of you right now is a graph that shows a comparison between speed and time. So this is a speed time graph. And the speed time graph, again, as you can see with the solid black line, is all over the place. It's not a nice straight line, which it should have been. And so we've put the green line in there to represent a line of best fit for that particular graph. So now we're going to calculate the slope of this line. So who here has already, without even doing any calculations, figured out what the slope is? He says 1. 0. Well, let's figure it out. Slope is, we've got our formula. Slope is rise divided by run. If you take a look here, what does this line not have anything of? A rise or a run? It does not have a rise. There's no rise at all to that green line of best fit. And so we would put our rise in there as 0. Our run could now be anything we want it to be. It wouldn't make any difference. 0 divided by whatever number is in the denominator is still going to be 0, right? 0 divided by 10, 100, 1,000, doesn't matter. So, you know, we could say, hey, we got a run of 1 second. So this is meters per second, and this is seconds. It doesn't matter. Our run is, our rise of that line is 0. And so that would be the correct answer to that question. So here's the next question. What does the slope of that line tell you? What does the slope of that line tell you? What is that? Well, in order to figure that question, does anyone know what it is right now? It's something we have not studied yet. And you may very well not know what it even is. But you could start to figure it out by looking at what units rise divided by run gives you in this case. So let's take a look at these units. So we've got 0 meters per second divided by 1 second. What is that answer? 0 what? What?
Yeah, that would only be 50.
No. Yeah, exactly. So it's not distance. So take a look. So in this case, we have 0 meters per second divided by 1 second, we said was our run. And so our units are going to be 0 meters per second squared. So what in the world is a meter per second squared? Does anyone know what those units belong to? Okay, somebody's going to grab their textbook a minute, find Unit B, Topic 1.3, the title, and tell me what that title says. We haven't studied this one yet. It's coming, but what is it? Not average speed. We've studied that one already. Who's got it? Exactly. So he beat you to the punch, Anthony. So, yeah, there you go. So it's acceleration. So if you could write this in your notes then, what does the slope of a speed time graph tell you? It tells you acceleration, and I think you kind of all have a sense for what acceleration is. It's speeding up and slowing down. And since this was constant motion, should there have been a speeding up or slowing down? No. And so that's why the answer is 0 meters per second, meaning there was no acceleration. Because those dots should have been being put down on that paper at a consistent, time interval and speed interval all the way along. There was no speeding up or slowing down, and so that's what that tells you. All right. Now we're going to do one last thing. What does the... Oops. So let's just kind of fix that up again. What does the area underneath your line of best fit show you? So we have not done this yet. So I'll get you to grab a pen and we'll kind of run through. So you got your line of best fit in there. So let's take a look at the area underneath this line of best fit. So we started at 0, and this is 0.5, 0.6, 0.7, 0.8, and 0.9, I think. Did I get those? I got those out of whack a little bit. So let's take a look at the area underneath this graph. So our last piece of data was taken at the 0.9 interval. So I'm going to draw a line up to my line of best fit at the 0.9 second interval. And we're going to look at this entire area underneath that line of best fit. What would that tell you? So what do you think? How do you find what? First of all, what shape does this area take on? A square. So how do you find the area of a square? Length times width, or side times side. So if it's not quite as, so we'll go to length times width. So let's take a look. Doesn't matter what we call it. Let's call this our length. Let's call this our width. So the length, so first of all, here's your formula. Area is equal to length times width. And we'll use our length as the y-axis. So what do we have? Well, we have 12. I'm going to call it, just because it looks like it falls right into 12 centimeters a second times, what's our width? 0.9 seconds. $8.5? No, because here now we're going to actually go with our original data, which says the last time the dot was put on the paper was at 0.9 seconds. So then I grab my calculator, and I'm going to figure out that area. So it's 12 times 0.9, and that will equal 10.8. Well, 10.8 what? What are my units there? Centimeters, because the seconds in the numerator and the seconds in the denominator are going to cross out, and I get centimeters. 12.8 centimeters. So what is that? What does the area underneath this line of best fit tell us? No? What is this? What kind of unit is a centimeter unit? Of? Distance. It tells us our distance traveled. It tells us that we traveled a distance. So guess what? Remember yesterday we had two ways to calculate average speed? Well, right here we have two ways to calculate distance. We could go back and use our formula. What's our formula for distance? Distance is? What is it? V times delta t? Okay, so we could take a look at our average speed, which is 12. And we could take a look at the time it took, 0.9, and we would get exactly the same answer. We would go 12 meters per second times 0.9 seconds, and we would get, using our mathematical formula, we would get that same answer, 10.8 centimeters. Okay, or we can use our graph and find it there too. So the area underneath, so write that down somewhere. The area underneath a speed time graph tells us the distance traveled. So graphing is actually pretty amazing because you can use, tells you the distance traveled, because you can use graphs to give you average speed, acceleration we found out today, and distance traveled. So I'd like to spend just a couple of minutes explaining again why units do what they do. Why do they cancel each other out sometimes, and why don't they, and so on. And it'll help you kind of understand this whole idea of why these graphs show you the things that they do. So here's the first example here. We'll just scoot up a little bit here. So in your notes, maybe this title, why do units cancel? And the whole idea behind why units cancel is pretty simple. You've learned it in math, and it's this. If the same unit shows up in the numerator and the denominator of something, they're going to cancel each other out. And by cancel, we simply mean that they're going to equal 1. Okay, they're going to become the number 1, which doesn't change an answer. Multiplying a number by 1, dividing a number by 1 doesn't change the number at all. So in that sense, we say they cancel. So here's another thing, just kind of to remember. In math, when you do 6 divided by 3, you get 2. But there's another way to kind of understand that operation, 6 divided by 3. 6 divided by 3 is really the same as 6 times 1/3. Because in math, you've all learned about multiplying a number by its reciprocal, right? Switching the denominator around and then multiplying by it. So 6 divided by 3 is 2. 6 times 1/3 is 2. So we've taken this number 3 in the denominator and we've changed it into its reciprocal. Do you remember doing that in math? Okay, good. So let's look at how the units kind of play in here then. So here's a formula you have. Delta T is equal to delta dV. So let's kind of put our units in here and see what happens. So we could rewrite 6, so if our distance is 6 meters, we could rewrite it as 6 meters over 1, because there's really a 1 underneath there. That 1 doesn't change anything, so we could write it as 6 meters over 1 divided by 3 meters per second, if that was our speed, 3 meters per second. So it's really 3 meters in 1 second, so we could rewrite it like that. And then you could take this denominator and write the reciprocal of it. But keep track of where your units go. So we would rewrite that as 6 meters over 1 times, and the reciprocal of 3 meters per second is 1 second per 3 meters. So we're going to switch that denominator around and make the reciprocal of it. And then when you multiply those two together, 6 meters times 1 second, you get 6 meter seconds. And 1 times 3 meters equals 3 meters. And then you can see we have meters showing up in both the numerator and the denominator, so we can cross those off. They cancel each other out, and you're left with an answer of 2 seconds. That's why that formula works. We can take a look at the acceleration and do exactly the same. We haven't looked at that formula yet, but acceleration is change in speed over time, or change in velocity over time. And so velocity would have units of meters per second, and time would have a measurement of seconds. And so if you look at the example below, you can see kind of how this could be rewritten, and then you would end up with the units of meters per second squared. So that's kind of a little quick explanation of why your units are doing what they're doing.